Our next speaker is John Holozak. John is a threat researcher on Carbon Black's Threat Analysis Unit, focusing on automation of threat detection and building out infrastructure for large-scale malware analysis. Within the field of threat detection and analysis, John specializes his research in binary classification, dynamic analysis, and reverse engineering. Here to talk about Bini is John Holozak. Let's all give him a huge round of applause.
All right. Cool. Good afternoon, everyone. Thanks for the intro. As Alex mentioned, my name is John Holozak. I'm on the threat analysis unit at Carbon Black, otherwise known as TAO. If you ever hear someone say TAO, it's referring to the threat analysis unit. And I'm here to talk about process emulation with a tool that we wrote called Bini. So before I actually get into it, we released Bini about 2 months ago now to the public domain. So just to show of hands, because I'm curious, who here has actually heard of Bini at all? Anyone? See a few hands. Anyone been able to mess around with it? I see one, I see two hands. Awesome. Perfect. So for those of you who haven't been introduced to Bini or been able to mess around with it, this will be a good introduction. The way I'm going to structure this presentation is basically I'll kind of go through the genesis of Bini and how we came about, kind of working through a problem that we had, came up with some goals and requirements, and then I'll start talking about a lot of the decisions that we made and some of the features that we built into Bini itself for process emulation. And then after a quick demo, then I'll actually introduce how to get started with it, because a lot of the feedback that we've gotten thus far on the tool is I'm not still entirely sure how you guys get started, even though we have a wiki and a nice README. So always open to feedback on that. So afterwards, if you're still confused, let me know. I'd love to continue to add information to the tool, especially the documentation side of things, so that it can get into more hands and more people can start using it. So in the world of security, we've always been looking at, for I guess a lack of a better term, binaries. And typically when we're looking at binaries, it falls under two camps, right? There's the static analysis side of things, where you are, say, running a tool against a file without actually running it, and you're getting a set amount of features, and that might have varying results. You know, if it's something that's obfuscated or encrypted, you're probably not going to get much information out of it. If on the other side of the coin, we have the dynamic analysis. In dynamic analysis, while you can get a lot more information out of it, such as behavioral indicators on top of any normal IOCs, it has a high time and cost analysis to analyze those binaries themselves. So often when my team is actually looking at binaries at scale, we often run into issues with actually doing things dynamically, just because we want to get as much information as possible, but it's hard to scale. So as we've kind of approached this problem, we started to think, well, what if we came up at it from a different way? What if we could take all the indicators, or a set amount of the indicators from dynamic analysis, and move it into the static analysis, and kind of increase the ceiling of features that you could get out of static analysis? Of course, that would address some of the core problems with static and dynamic analysis, such as I already mentioned, obfuscation. Anti-analysis is always in a lot of malware, especially when you're trying to deal with dynamic analysis. It's hard to keep up with. It's always been a cat and mouse game in that regard. And when you're trying to do malware analysis at scale, like we're attempting to do, not all malware is going to react the same way to a standard environment. So in our lab, where we're doing a lot of dynamic analysis, is we are actually taking just a standard image and then running malware against it. And so say it's a malware that requires a very certain piece of, say, a certain software that needs to run before it will actually do anything. Well, we might not have accounted for that, because we're trying to make basically a massive image with as much software as possible. And at that point, it becomes kind of a sunken cost fallacy, because we're trying to just keep up with all these different software that malware might need to run, and so why are we just continuing to add software to, say, a standard image for dynamic analysis? So as I mentioned, our goal with actually creating Bini is moving a lot of those dynamic indicators into static time and for static cost. And so with that, we want to reduce so as I mentioned, we want to reduce the cost, and we want to do this at scale. We obviously are not, on our team, are not a huge group of incident responders, but we do have a lot of threat researchers who have worked in the incident response space. So another aspect that we also want to consider is how do we want to triage malware in a timely fashion. So obviously if you're looking at dynamic analysis in, say, an IR engagement, you might have a number of malware that you need to get information out of stat. And in some cases, it might be super obfuscated. It might be looking for certain software. You might have to start reverse engineering and patching binaries just to get it to run, and that can be a very involved process. So the idea behind that is to kind of get rid of some of that overhead and step away from the actual patching side of things, the reverse engineering as much side of things, and start moving a lot of that into the triage time space. And so the way we arrived on how to do that is through emulation. So we've actually built this tool on top of Unicorn and Capstone. And we're basically extending these libraries to start mocking out OS level functions, system calls, and a number of different subsystems, such as like the file system, the registry subsystem, etc. And by taking these, we've actually built up upon a tool that we think would be helpful for both analysts, IR professionals who want to actually start doing more triage in a timely fashion, and also the researchers who want to start doing things at scale. Of course, this isn't the first time this has been attempted. This list is actually quite short. If you go over to the Unicorn Engine Showcase website, they have a number of emulators out there. But specifically in the world of portable executables and Windows, PEs have had varying luck with actually getting a full emulator going. In many cases, some of these, as far as we could tell, were just made to emulate shellcode, for example. Or they went as far as to implement a PE parser, load in the PE into memory, and then maybe start from the entry point of the PE itself. So we wanted to actually extend that further. And so that kind of brought us into our requirements of what do we want to add and extend from current emulator work. Obviously, with any sort of emulator, you need a way to parse PE files so that you can actually load them into your emulator, hit an entry point and go. We also wanted to expand past that and start emulating and mocking out API calls in the Windows subsystem. So say there's a call for like sleep, for example. So that's an anti-analysis technique that if you're trying to do dynamic analysis, a sample might try to sleep for, say, 20 hours, and then you hit the cutoff for your dynamic analysis, and then all of a sudden you don't have any information because it was sleeping the entire time. So with API hooks, we can then hook and define our own implementation, and then say if it calls sleep, we say, okay, we slept for X amount of time, but what we're really doing is just increasing the clock and increasing the CPU cycles on the emulator itself to make it look like the sleep happened, but in reality it happened in a split second. So we're actually not waiting on that sleep forever, for example. Aside from like a hooking system, we are also building out an OS subsystems. So I mentioned like the file system, the registry system. We started to emulate out a lot of the userland process structures, so like the TIB and the PEB, which I'll get into those a little bit later. And obviously some sort of memory management utility, so something to handle our heap that we've got kind of built on past a normal heap besides malloc and free and all that. And we want this to be configurable. So with a lot of different dynamic analysis runtimes or tools, you might have an issue where you need to define different systems. And so if you're dealing with, say, a malware that might behave differently on Windows 7, Windows 8, Windows 10, you want to be able to quickly swap those out and define environments with, say, different registry keys, different keyboard layouts, etc., so that you can swap those out quickly and then see how it reacts to those different configurations. So that was another goal of ours, was to actually build that in, and I'll get into that a little bit later. So now that we actually have a goal to achieve and requirements to fulfill, that brings us to Bini. So the rest of this presentation up until the demo is basically going to be a loose journey of how we kind of built in a lot of different features into Bini itself. This was originally started as a POC that we just kind of ran and kind of hoped for the best after, say, a month of work, and then we found out that it was actually useful, and we were actually getting good information out of it, even in its very minimal form. So from there, we just started building on this tool, and it became a journey of just adding more and more features, and we're still adding features as time goes on. So obviously, the first thing that we need to do with any emulator is actually start parsing PEs and DLLs, and map them into memory so that we can actually reference that memory when we're emulating the process itself. So obviously there's a number of libraries out there for parsing PEs. In the case of Bini, Bini is written in Go. Go itself does have a PE parsing library, but we actually opted for something else because we took on a different kind of a different path aside from just parsing the PEs themselves. So the way we wanted to approach this was we read in the PE itself, parse it in, and then we might parse in any sort of linked DLLs that are associated with it. And then from there, we update all of our memory addresses, relocations. We start updating our import address table and maybe our exports and any other lookup tables. And then from there, we then put everything into memory. So that's actually a little bit of a difference than the actual Windows loader itself. The Windows loader will actually build in PEs into memory as it goes, and then it'll just keep parsing and adding onto that memory. We're building the entire object that we need in the emulator first, and then putting it into the emulator itself. And I'll get into why that is in a second. So once we actually started implementing PEs and DLLs, the parser for it, we actually ran into a bit of an issue. So turns out starting in Windows 7, I believe, Microsoft added API sets and their schema to Windows itself. And what they are effectively is just another abstraction layer over DLLs, so that when you call, say, kernel32 some function, it's actually reaching into what's called the API set schema.dll, which maps to another DLL elsewhere. And the reason for that is that Microsoft's trying to move away a little bit from the kernel32 kind of naming scheme, so this is their way of kind of a stopgap measure to do all that. Luckily, it's actually been quite documented, not by Microsoft themselves, but Jeff Chappell, who actually on his website kind of went into detail on how they work. So his work was actually pretty helpful in us kind of implementing this, being able to parse these in and improve our lookup. Improve our lookup. So once we actually had our API sets that we were able to load, we were able to start loading it. So we parsed in PEs and DLLs. We then went and were able to parse API sets, and we're actually start to call different functions with some success. But we were actually running into an issue where we weren't running this on Windows itself. So at first, we were actually building Bini within we were building it within Linux and Mac OS. So that's one of the cornerstones of Bini is that it's cross-platform. And that's kind of why we chose Go, is because it's statically linked and we can compile it for any operating system itself. And so we had to actually look at a hooking system, a proper hooking system. So that was like the next big thing that we started to work out once we were able to load a PE in and hit the entry point and go. So at that point, we've reached feature parity. So with a hooking system, we actually have to ask ourselves, what is the minimum amount of information that a malware needs in order to continue? In the case of this, create file A, which is a kernel32 call, the handle for the file needs to be returned in the EAX register. So we need to actually emulate that if we were to, say, re-implement create file A in our emulator itself, and return what the malware might expect. So that brings us to basically a lot of requirements for hooking itself. So we basically ask 4 core questions. The first is, do we have a map of the name to the real address in the emulator? So in the case of the last example, we should have a name of create file A in our hooking system, and that maps to somewhere that when called, it'll jump to either our implementation or the original implementation. And what is the calling convention used? So in most cases with the Windows 32 API, it's standard call, so that's usually pretty easy to answer. We usually then ask how many parameters are being passed in the function, and oftentimes this is documented. If not, it's just a quick, load it up in IDA, etc., and then you can see how many are being passed. But in many cases, we want to actually get named parameters so that we can actually get fidelity and introspection into what is actually being passed into the function itself. And if there's any return value, what do we want to return? Do we want to let it return what it would normally return, or do we want to return something else? So back to my sleep example from earlier, we could hook that and just say, hey, return, yes, I slept for 20 minutes, and then kind of move forward. So to fulfill a lot of those questions and requirements, we kind of attempted 2 different ways of creating a hooking API for Bini itself. The first is a full hook, where we define the implementation. Typically, a hook in this case, and this is the example from earlier, we define the parameters, which are listed in the Microsoft documentation, so DW milliseconds, and then maybe an implementation on top of that. So in this case, all we're doing is just increasing the ticks for however many milliseconds are passed in, and then we're telling the emulator skip over the original function call and do ours instead. So we're returning success, and the emulator has then moved forward. On the other side of the coin, we also have the partial hook, which is basically just a pared down full hook. The idea behind this is we still want to get the parameters, and this is actually a bad example, unfortunately, for these 3, but from there we'll be able to get all the parameters that would be passed in and have introspection into the function itself, but it'll still run the original implementation. It'll actually load up the DLL itself that's being called, and then run that implementation instead. And the reason why we're still calling this a partial hook and actually still listing the parameters, even in this poor example, is mainly for stack alignment. So if we're not listing parameters, our emulator has no indication of how to actually realign the stack after all said and done, especially if there's a full hook involved. So if we don't pass any information, if the assembly itself is actually passing in information, and we're not accounting for that, then the stack gets all messed up, and then the emulation fails. So this is just another example of how we kind of get introspection. So we add, on the first line there, you can see that we added a hook, and that hook has 3 arguments. So destination, character, and count. That's just a simple memset. And then the output in Bini, when you run it later, is down below. So the way you would read this is you have the thread ID in the brackets, and then you have the memory address in the emulator, and then whether it's a partial or a full hook, P or F, and then the name of the function, and then you get to see all the values passed into the function itself. And then here's a full example of it in action. So this is Bini's verbose output. Typically, Bini will only output function calls, but in this case, I passed a -v, and it'll actually show every single instruction up until that point. So I guess the important parts to kind of key in on here are the highlighted lines on this. So now that we've actually gotten through probably the boring part of it, just parsing PEs, DLLs, etc., building a hooking system, we actually get to do a lot of the cool stuff that allows us to run PEs on many different systems, emulate them, and get information out of them. So as we went on, we started to encounter different malware samples that were doing certain things with, say, the file system. Or sorry, I'm ahead of myself. So one of the things that we did, and I mentioned we would get into this earlier, is we started to run into malware that was actually accessing user land structures. We had not implemented those yet. So things like the TIB, the PEB, K-shared user, those were not implemented, and we needed a way to actually support those. So we never actually implemented segment registers up until this point, and this was kind of the turning point when we started to look at, okay, maybe we should start building in actual OS functionality. And from here, we actually built up segment registers, and thanks to Chris Eagle, who I believe on the Unicorn website had an example of this running in a different language, but we were able to take that and kind of use it for our implementation, which is pretty nice. We actually moved past that problem pretty quickly. So once we actually had segment registers, we can support things like the TIB and the PEB. We started from here. We just started to kind of fill out these as needed. We kind of faked everything. So for a good while before we actually started running into issues, we hit maybe like the first 5 to 10 fields within the TIB, and then we would just kind of fake those, and by putting in some reasonable values, and then it would, the emulation would continue further. And so that indicated to us that our segment registers were working, our user land structures were working, and things that were expected out of the OS itself were actually being returned properly, and we were able to continue emulation. So at this point, we've got a lot of the core functionality now. We started to have the basis for building out even further the OS subsystems themselves. We're starting to mock out the OS. So the first thing that we did once we were able to actually emulate the TIB, the PEB, all the other user land structures, is we started to mock out the file system itself. So going back to our slide earlier with create file A, obviously the malware expects the handle returned in EAX, and what we did was we implemented a memory manager to support this, so that if there's any sort of call to heap, then we intercept it on the emulator side, and then from there we can actually get back a valid handle, and then continue doing, say, some sort of file system interaction or registry interaction. So after that, we started to have our actual full hook of anything that was related to file system. So with this, if there's any sort of create file handle on the emulator side of things, we actually jump out of the emulator and into Bini itself, and then Bini with its full hook system then handles the lookup of the handle in the lookup table, and then from there can actually intercept the create file call and actually create a temp variable on the file system itself, which is pretty nice. In many cases, it's just in the temp folder, which is by default. We can actually define that elsewhere in our configuration files. Sorry, I kind of lost my spot here. There we go. Just gonna hit myself. So once we actually have our handle and we're able to create a file, then we can actually write the file to disk. And so when we're writing the file to disk, we tell the emulator itself, hey, we've written this file to where you said, so hey, you requested C Windows System 32 for it to be written there. But what's actually happening is we're writing that file to the temp directory, and then from there we can actually pull that information for, say, further analysis. So if it's dropping another DLL, if it's dropping another EXE, what have you, we actually have full view into that, and actually show that off in the demo here shortly. The registry is kind of in the same vein as the file system. Again, basically it just expects success. We full hook anything to do with the registry, and then we kind of keep track of that on the Bini side of things rather than in the emulator. And so if there's any sort of opening of a key, or a reading of a key, or a writing of a key, we actually can keep track of that and kind of intercept anything that has to do with that, which is a great segue for the actual configuration files themselves. So configuration files in Bini are basically just YAML files that are defined. By default, I believe, do Windows 10 32-bit. We also have, I think, Windows 7 32-bit as well now. But you can define where your OS DLLs are actually located. So in this case, you can see OS Win 10 32-bit. So any DLLs that might be associated with your emulation, you want to drop those in there, and then it'll use those for any sort of partial hooking or system calls. From here, we're actually able to define our registry as well. So this is where the power of the configuration files that I mentioned earlier comes in. So the registry itself, we can actually define, and we can actually pull all this information in just out of copy-paste out of Regedit itself. We can define multiple of these configuration files, and then have different runs of, say, the same malware depending on whatever registry keys we have set in those configuration files, which is pretty nifty. If you take, say, something that's expecting a French keyboard layout and you run the malware through Bini, it might have a much different outcome than if you had, say, an American keyboard in your registry. So the two configuration files that you could define would just have a registry key for whatever keyboard layout you have, for example. So now that we actually have a file system, a registry system, some sort of memory manager, as I touched on earlier, we basically have a mock OS kind of built out. Everything we could need at this point is basically done. So we started running a lot of samples. This is about the turning point in Bini's development, where we took a lot of samples and started throwing it at Bini itself. We have a full research lab where we just kind of take everything and set it up in an automated environment. And so we were running a lot of samples, particularly like the Ember dataset, against Bini to see what was coming out of it. And so we started to run into samples that were expecting some threading. This is not something that we actually anticipated. Well, I guess we did anticipate, but we never actually built into Bini itself. And so the mocked threading, we create a mock threading manager that would basically just round robin through each of the threads. The way we accomplished this was we just said, hey, for every n number of instructions that you hit in a thread, then context switch to a different thread. That's all we really did. There was nothing fancy about it. And that allowed us to basically kind of kick the can down the road on the threading aspect of things, because in most cases, malware doesn't really care about all that, about the timing of everything, as long as it gets the information at some point in whatever thread. So if it's waiting on something, it's properly implemented with proper threading attributes, then it should just work regardless of the timing of how threads are context switching. And so that brings us to like the last big thing that we've built into Bini most recently. And so we built in basically DLL main execution to Bini itself. And the reason for that was we hadn't actually been doing that yet. Up until this point, what we were effectively doing is taking PEs and DLLs, loading them into the emulator and pressing start and saying, go ahead, maybe it'll work. Turns out that if you're missing the DLL main portion of running a PE, it's supposed to run through the DLL main before it actually runs the PE itself. You're probably going to be missing a lot of information, especially in the user land space. So in the case of this, we implemented DLL main. The way we originally accomplished it was we would basically set the entry point to a DLL, run it, and then the return address of that would be pointing to a different place in memory, and then which would have an interrupt, and then we would pause the emulator, load up the next entry point of the next DLL, and then kind of continue from there. Turns out Unicorn doesn't like that so much, so we actually moved on to our next solution, which was ROC gadgets. And so the way we accomplished effective loading of all the DLL mains for emulation was we essentially just set the entry point to the first DLL that would have been loaded, and the return address of that would just be the next entry point, and that return address would be the next entry point, and so on and so forth. So we were able to actually do a lot of that, which do a lot of the DLL main stuff, which is pretty awesome. Demos. So without further ado, So this is just Bini running. You can see we also built an API set reader for us, so it'll actually read the current API set that you have set in the configuration file itself, and so it'll run through that. And then we're running out of time, so I will try to skip ahead a little bit. We also have a -d flag, which will show the DLL which is being run. Looks like we are not actually playing. It'll show the DLL actually being run, the function that the DLL is using. Or sorry, the DLL that the function is in. So in this case, a lot of kernel 32. And then this is where we actually run some malware that drops and creates a file to disk. You can see create file A, it's dropping another exe to disk. You can see it writing the file. And then if we look at our temp, it's dropped there. And this is just a poor example, but we have the malware itself. Yeah, it says hello world, I guess, in the file itself. So not a real exe, but it just shows off that functionality in a test thing. We also support JSON output. So for those of you who want to build on top of Bini itself, you can get all the JSON output line by line. So same output, you can just parse the JSON. Now for some real malware, real quick. Now, this is actually very, very quick, as you can see. This is a full emulation of something that runs a service, so you can see the service name being written there. So there's a behavioral IOC of a new service that's being started up. So that's what this malware here is doing. I believe if this is the same one, it's also creating a file and dropping it to disk. But for the sake of time, I'm going to pause it and basically get into how you can get started with Bini. So this is a big question that's been coming out of a lot of people, and that is, how do I actually get started with it? So as I mentioned earlier, it's written in Go. If you want to get started with it, feel free to fork or clone it. We have it on GitHub available for anyone to access. We have a built-in Docker file, which we actually recommend you use because it uses standard versioning for a lot of the libraries that we use, such as Unicorn and Capstone. Capstone itself, we had some issues with version 4, so we had to actually start sticking to the Docker file. So if you were to ever make a pull request, we ask that you test it in the Docker file itself, and then we're actually certain that it's probably going to work. So the way it works, and the README and the wiki will get into this, is you need to import necessary DLLs. We only support Windows 32-bit right now, so 7, 8, 10, etc. We've had a few people try to load in WoW64 stuff from 64-bit Windows versions, and that hasn't worked out very well. And so we've always had to kind of walk people through that. At that point, you can just start gathering your malware samples and running them in Bini. And if there's any sort of missing hooks, then you just run them against it. You implement the hooks, and then you run it again, continue, rinse, repeat. And then send a pull request if you have any hooks that you have implemented. So in the case of this, we have an output. I forget the hash exactly, but basically, with the 2 stars there, we're missing search path A, and so we just need to implement that as a full hook. We go to the MSDN documentation. We see, okay, here's all the functions on the left-hand side of the screen there, and on the right-hand side, you have your return values. From there, you can then implement your full hook. This is just a lazy full hook. It actually hasn't been pulled into Bini itself yet. I think it's sitting in a branch right now. And then now that we actually have it implemented and we run Bini again, you can see search path A is now capturing all the arguments. So it's trying to search for rpawInet.dll. And then we run into yet another hook that's missing. So it's kind of like a rinse repeat cycle. Just implement your hooks, and then you'll be good to go. So we've open sourced this. Basically, we're just increasing the fidelity with a lot more hooks. please send us PRs, and we have a lot of other long-term projects, so that's about it.